Whether we are looking through a microscope, running a clinical trial, or scanning the horizon with radar, we never get to see reality perfectly. Every instrument we use to measure the world is swimming in a baseline of random noise. This creates a permanent, physical barrier between the underlying truth of the universe and what we are actually capable of observing. We don't measure reality directly. We measure a proxy for it, and that proxy is always flawed. Because every measurement happens under this cloud of statistical uncertainty, every time we test for something, a disease, a weapon, a signal, we are forced into a matrix of 4 possible outcomes. 2 of these outcomes represent success. A true positive means we detected a signal that actually exists. A true negative means we correctly ignored noise that was just noise. But the other 2 outcomes are failures. The first is a type 1 error, commonly known as a false positive. This happens when our system incorrectly rejects a true null hypothesis, hallucinating a signal where there is only static. The second failure is a type 2 error, or a false negative. This occurs when our system fails to reject a false null hypothesis. The signal is real, but it is too weak, and we miss it entirely inside the noise. Because these 2 errors are inescapable, statisticians operate by a strict maxim: an absence of evidence is not evidence of absence. Failing to detect a signal does not guarantee the signal isn't there. The objective of rigorous scientific design is never to build a system that perfectly eliminates all error. That is mathematically impossible. The objective is to build frameworks that quantify the error so we can control it. To see how we actually measure these errors, we can look at a trial comparing a new diagnostic test for tuberculosis against a gold standard PCR test. This chart shows the results of that trial mapped onto a 2x2 grid. On the top, we have the underlying truth of who actually had the disease and who didn't. On the side, we have the test results. The data sorts neatly into our 4 categories: true positives, false negatives, false positives, and true negatives. If we isolate the column representing people who actually had the disease, we see 142 tested positive, while 14 slipped through the cracks. By dividing the true positives by the total number of sick people, we calculate the test's sensitivity, in this case 91%. This is the exact mathematical probability that the test will detect the disease when it is truly present. We run the same calculation on the healthy column. Out of 1,344 people who did not have TB, the test correctly identified 1,336, generating 8 false alarms. This gives us our second metric, specificity, which sits at 99.4%. This represents the probability that the test correctly rules out the disease when it is completely absent. If you combine all the correct diagnoses and divide them by the total number of patients, you arrive at the overall accuracy, often called the percent correct. These high 90s look impressive on paper. They give the impression of a precise, definitive machine. But sorting complex biology into 4 distinct boxes creates an illusion that hides the actual mechanics of how a measurement works. The flaw of a 2x2 grid is that it treats signal and noise as entirely separate categories, as if a patient is either glowing red with disease or completely clear. In reality, biological markers, radar signatures, and protein concentrations are continuous variables. The data generated by healthy people and sick people will always form 2 distinct bell curves that overlap. Because the test needs a definitive yes or no answer, engineers draw an arbitrary threshold somewhere along this axis. This line is the decision criterion. Anything to the right triggers a positive diagnosis. Anything to the left is negative. The healthy curve bleeding to the right creates false positives. The sick curve bleeding to the left creates false negatives. This overlapping geometry means the 2 error types are mechanically linked. If you slide the criterion to the left to catch more of the sick patients, you capture more of the healthy curve along with it, mathematically forcing an increase in false alarms. Slide it right to reduce false alarms, and you guarantee you will miss more of the actual disease. A false positive or a false negative is not a malfunction of the machine. They are mathematical inevitabilities, dictated entirely by where the designer chooses to draw the line. When human lives are on the line, the placement of this threshold becomes a highly calculated equation based on the asymmetrical costs of making a mistake. Let's consider how engineers tune the sensors in an airport security scanner. Aviation security operates with an extreme leftward shift on the curve. It is calibrated for maximum sensitivity because the cost of a false negative, allowing a weapon onto a plane, is catastrophic. To maintain this tight security, the system intentionally generates a massive flood of false positives. It alarms for belt buckles, loose change, and foil wrappers. That friction isn't a glitch. It is the operational tax we agree to pay to prevent a catastrophic failure. The criminal justice system faces a similar threshold problem, but its curve is tuned in the exact opposite direction. The legal standard of proving guilt beyond a reasonable doubt places the decision criterion as far to the right as possible. The system demands incredibly high specificity before issuing a guilty verdict. In practice, this means the legal framework intentionally accepts a high rate of Type 2 errors, allowing guilty people to go free, in order to ruthlessly minimize the societal cost of a Type 1 error, which is locking an innocent person in a cage. Our systems are built around these specific trade-offs. The error rates we tolerate reveal the moral priorities and risk tolerance of the society that engineered the system. Because thresholds can be manipulated so heavily, evaluating any system purely by its overall percent correct is a statistical trap. We can see this breakdown in a trial comparing human doctors against an automated algorithm designed to recognize tumors in X-ray plates. This table summarizes the results. Both the doctors and the algorithm achieve an identical overall accuracy of 80%, but looking closely at the false alarms reveals a discrepancy. The algorithm has a false positive rate of 38%, almost double the doctor's 20%. If both diagnostic methods are technically 80% accurate, but the machine triggers nearly twice as many false alarms, how do we determine which one is actually the superior detector? The percent correct metric fails here because it mashes two completely separate variables into a single number. It confounds the true sense and capability of the detector with the subjective bias of where the threshold was set. To evaluate actual performance, we have to strip away the human bias. We need a mathematical metric that isolates raw discriminative power from the noise. To solve this exact paradox, psychophysicists use a framework called signal detection theory. This theory brings back our overlapping curves of signal and noise. By analyzing hit rates against false alarms, we calculate the discriminability index, or D'. This metric represents the physical distance between the peak of the noise curve and the peak of the signal curve. While sliding the decision threshold left or right will alter how many false alarms you trigger, it cannot alter D'. The baseline separation between the signal and the noise remains locked in place. To resolve the X-ray paradox, we convert our percentages into z-scores, standard deviation units that measure how far a result sits from the mean. Even with a high false alarm rate, the machine's 98% hit rate creates a much larger statistical gap from its noise curve than the doctors achieved. This yields a D' of 2.35 for the algorithm, compared to only 1.68 for the humans. The machine is objectively the better sensor. It was merely operating with a heavily biased threshold. If you want to genuinely improve a system, shifting the threshold around won't help you. You have to invest the resources, better sensors, larger sample sizes, higher resolutions, to physically pull those overlapping curves further apart. True empirical mastery does not mean achieving zero errors. It means maximizing D' to isolate the truth as cleanly as physics will allow, and then deliberately placing your threshold to survive the errors you are mathematically guaranteed to make.